Hello, very good afternoon to you all. So you are welcome to our second session. Dr. Chandra sir, please proceed for the second session.
Yes, sir.
Yes.
Okay, I'm sharing my screen.
Yes, sir.
Visible?
Yes, sir. Visible, sir.
Okay. So, good afternoon, all. So, in this particular session, we will talk about the third type of the machine learning technique, that is the reinforcement learning. And if we combine it with the deep learning, so it's known as deep reinforcement learning. So, we will try to see the various applications of the deep reinforcement learning and its application in different fields. At the end, we will discuss how it can be used in the medical field as well. Right. So yesterday we talked about this learning, that it's a way to interact with the environment, and the environment give some rewards or punishment. Right. It may be by looking at the other agents. So this is learning. We will talk about the reinforcement learning. So in that we discuss about the supervised learning. We take some examples, then we test that example using the previous existing supervised learning techniques such as the SVM, neural network, and others. Then we talk about the unsupervised learning in detail, where we see how to classify or how to cluster the data points into different groups. Today, in the morning session, we talk about how to generate the new samples using the unsupervised learning technique, GAN method, basically. Now, the third one was the reinforcement learning or the self-learning. So in this, the agent, uh, it interact with the environment, external environment, and the external environment give the feedback. So there is no input in this as such. So whenever I take some decision, the environment give me some rewards or punishment. Right. So, but with this deep learning revolution now, we are having the one more advanced version of the machine learning technique. We call it as a deep learning. So we try to mix that, we try to upgrade all the existing techniques using this deep learning. And this deep learning actually is possible because of the high computational power. It's not like that the idea was not there. Yes, the idea was there, but at the time we were having the limited computational capability. Then the algorithm we have developed according to the deep methods now, different variants of the CNN in today's world. The best, so that it can give the best result on a given data set. The size of the data set is also very, very huge nowadays, right? So this ImageNet, it started somewhere in 2009, a competition that is being carried out every year. So in that, the people, the universities, the companies participate all over the world, and there were around 22,000 categories or classes in this particular data set. So we are having a very, very large amount of data set in today's world. So we try to learn from that data set, and then we see that how we can use it for the different applications. If I talk about with respect to the vision based problems, then uh, there was a time when the error in 2010 was around 28.2%. This was a very huge error, but with the advent of the deep learning methods, right, in 2012, AlexNet, first CNN model, then it got reduced. And in today's world, we have achieved error. We have reduced this error to 2.3. While as a human, our error is 5.1. So now we are in the stage where we can say that computers work or the machine, they are better than the human now, right? So if we combine the deep learning along with the reinforcement learning, then it's deep reinforcement learning, and it is a framework for learning to solve the sequential decision making problem. So basically reinforcement learning was used earlier for that only, but now it has wide applications. Again, I will say that this reinforcement learning was not that explored for the real-time applications. It was limited to the game-based applications only. Now the question is why actually we need a algorithm for playing for games, because games are a way of representation, right, to solve a complex problem. So we develop the new approaches in that, new strategies in that, and then accordingly we take the actions. For example, if I want to play tic-tac-toe, then there are 9 states, only 9 states are there, considering 3 by 3 metric size. And if I want to solve I want to play, I want to make a bot for the chess, then I am having a larger samples, and there are some rules in it. So constraints are there. So accordingly, we try to formulate the new algorithms, right? So this deep reinforcement learning come into the picture, or it got popular after this AlphaGo in uh, somewhere around 2013, right? That it give this option to the researchers that yes, now we can use reinforcement learning for solving some real-time applications. Now all over the world, people are working on the different fields. In MIT, the people are working on the deep traffic using the reinforcement learning methods, deep reinforcement learning methods. Other researchers, they are also working on the motion analysis, as you can see in this next second diagram, using the reinforcement learning, that what should be the I will say musculoskeletal environment where I can develop a system so that my robot can work or can walk without falling. Right, so it has various applications, not only in these fields. It can be used in the electrical field as well as in the finance field or also. So in supervised, the main, I will say, think over there, the main rolling factor is the loss function, right? Because based on this loss function, we can tell, we means the supervisor, the environment may tell how good or bad, and then accordingly we adjust our value. So the value may be 1 or 0 in that case, right? So we know the value, we know the output in that case. While in case of reinforcement learning, there is nobody who tells that it is correct or not, right? But we learn through the experience, right? So supervised learning is teach by example, while the reinforcement learning is teach by experiment, or by experience. You have to understand the nature of that particular problem, and then accordingly you need to decide which learning algorithm you should use. So reinforcement is actually a way of repeating the same task again and again. And reinforcement learning is a programming agents. If we try to learn the agents are nothing but your intelligent program, right? So it's a way of programming the agents with the help of rewards and punishment, without specifying how the task to be achieved, right? So it's all depend on the feedback without providing the standard of the correctness in that. There are certain arguments that reinforcement learning is again kind of unsupervised learning, but I will not go in detail of that, or supervised learning. It's a different learning. So people are working are considering reinforcement learning as a different way of learning, because over here we go by the rewards and punishment, good or bad, and my agent learn by receiving an agent by a reward through the trial and error. Because if no information is given to you, the first step is we go through trial and error, right? And we try to interact with the environment. Then based on some feedback, I try to adjust my policy. So the best example of the reinforcement learning is the way we walk, because we learn ourselves, right? One way or another way. So it's an open question that how we learn to walk, with a very few examples of trial and error. Right. So the possible answers for this is that either we have developed our hardware, that is our body, in 230 million of years of bipedal movement, right? Considering all the organism in that, then maybe possible that we are good in copying the others, right? Or we have developed some good algorithms better than the backpropagation and other existing algorithms. But still this it's open question how we walk, right? So this reinforcement learning is similar to that only. It is very close to human. Agent learn a policy of how to act in a given environment based on these rewards only. So the example is, let's say, riding a bicycle. If I want to learn how to ride a bicycle, and if my parents are with me, my brother or sister are with me, my friends are with me to help, right, to ride on the bicycle, then it's kind of supervised learning. But one day, let's say you decide yourself that, okay, no, today I will learn myself, right? So it means you are moving toward the reinforcement learning. So it's hit and trial. So how we will go proceed in that? Randomly, we will select any side, left side or right side, and then we, if we fall down, then we realize that, okay, this particular angle is wrong. So let's try with some other angle, 60° instead of 45. Again, I fell down. So I repeat this task till 70, 80, then okay, I concluded that, okay, this particular side is wrong. Let me try right side now. So again, I tried the different angles. Again, I fell down. And with time, I reached a particular instance of 90°. And at that time, I was able to ride my bicycle without falling. So in this particular experiment, what we did, we learned from our own error, right? So we try to build a experience matrix. So let's say, let's make a experience matrix for bicycle learning. Right, my computers, they are good with the computational, and the best way to represent an information is through graph, right? So through matrix. So this is my matrix where my my rows are the actions, and my columns are my states. So from one state to another state, in this particular case, your state and action are same, left, right, and straight. And throughout my different episodes, episode means the one whole observation, one whole game is considered in reinforcement learning as one episode. In the other learning, we call it as epochs. So over here in the one episode, I learned that when I moved from left to left, then I fell down. So I updated my table as 2. When I moved from left to right, I updated it with a higher value as compared to the previous 2 values and 8. Now you are free to fill any data over here. I can fill -2, -4, and sorry, -2, -4, or 0 at least. But it should be in the incremental order only, as per the goodness of that particular action. So with time, this particular matrix got saturated, right? All the values will saturate in that. So I can conclude, okay, now I can say that I am an expert in that field. It means your that experience matrix has filled now. Right. So I will say that this is very close to human, because throughout our life also this is what we are trying to do. We try to take experience from the different projects, different machine learning techniques, different occasions. So throughout our whole life, we are trying to fill the values of our experience matrix on. And with age, my this experience matrix got saturated. And at the time I can say, okay, I am good in this particular activity, I am good in the machine learning, or I am good with the driving or some other activity, right? So let's see how to build this matrix for the as a programmer, for the agents, for the intelligent programs, right? So my environment is there. So the open question is that how or what can be learned from the data, right? So first let's gather that data. So how we can gather the data? This is the uh, structure of the agent. I hope all of you are aware of the agent, that this is in the agent we have the some sensors. Then based on those sensor, it can take some action. These are the effectors. Then it interact with the environment, right? Take some actions, and then got some actions on some feedback on that, right? So let's say I need to make one automated car, right? Driverless car. So I need to first see what should be the sensors in it, what how I can collect my data. So the sensors may be your GPS, IMU, your lidar, your camera, radar, microphone, and other things, right? Once I gather this data, sensor data, then the next thing is I need to extract the features, right? So I can go with the traditional or shallow features, shallow learning methods, that is the SVM, decision tree, or I can use the deep learning method where automatically extract the features, right? So then once I am having those features, then I need to represent them, right? One-to-one representation is there, or one to many, many to many. All these are there in the features. So it may be possible that for many features I am getting one output. For one output, I'm getting one. For one input, I'm getting one output, and likewise. Now, from this, after this representation, I can use the different machine learning technique accordingly, and I can get the knowledge. I acquire the knowledge. So let's say for this image, I acquire this knowledge that in this particular image, a duck is there, right? And I also acquired this knowledge that the sound of the duck is like this, right? This is the sound. So if I want to apply it for a particular activity recognition, so in that case, I give this reason also, that why I am calling it as a duck, right? Because of the sound, because of the similar structure, and likewise. Now, once I am having all this knowledge and reasoning, then it should be applied to the real time. So for that, I need to apply some applications. I need to perform some planning so that my agent can take some actions, right, using that effector. Now, if we combine so in case of this sensor to knowledge, it is the part of the deep learning nowadays. And if we apply the reinforcement learning, basically this planning action, all these apart come under the reinforcement learning. So combination of both, we are able to solve the real-time applications, right? Let's see how. So in reinforcement learning, we have the agents with us. We execute the action, then it observe a new state and receive some rewards. Right. So we need to see that what cannot be modeled in this way, because there are certain applications. It depends on the application to application. What are the challenges in learning in this framework? The major challenge is that I need to train my system. So for that, I need large either simulation modeling or some data, right? So some elements in the reinforcement learning are your agents. Then agent interact with the environment based on certain policy. That policy may be your greedy based on non-greedy. These are different type of the policy we will talk about. Then correspondingly, I got some action. I have to take some action, right? Then based on the interaction, I got some reward function. It defined the goal in the reinforcement learning policy. So value function is there. So as I told you that there are different type of environment. So the environment may be fully observable. For example, your chess. So in chess, we know all the possible states, right? While in case of poker, it is partially observable. Atari game is your single agent based, while your deep traffic, where a lot of other cars are also running on the road. So in that, each car act as a multi-agent, as an agent, and overall we call it as a multi-agent based system. Your card pool is a deterministic system where there is no randomness. While in case of deep traffic, it is stochastic in nature. Why? Because maybe possible some pedestrian may come, some cow may come, or something like that. Right? Random probability distribution is there. No sequence of the pattern are there. Similar to that, we can divide the environment in the static and dynamic, discrete and continuous, right? So based on that, we have to identify, we have to develop the policy, value function, and model. We need to develop a model for this representation, right? So that state can be changed. So for any particular state, I have to perform one action and I will get a reward. So for state 0, I am having these A and R value. For state 1, I am having another state and the reward value, and likewise. So let's talk about the policy now. So if this is my starting state, I'm considering this as an arena where I know my whole states in that. So here I cannot move, right? There's no path from here. If I move to this -1, then the reward, then the punishment is very high, -1. And my aim is, this is my end goal, +1. So I need to reach to this particular state. Now the question is, what should be the modeling? What should be the value of state and action pair? What action I should take and what policy I should follow? Right. So let's say my rewards are -2. Means for going for taking the correct solution, my reward is -2. So in, because this is kind of minus 2 means negative reward. So the policy that I will follow over here is the shortest path, because I don't want to waste time in the more number of the steps, right? So these are the possible actions that 80% of the time I can go move up, and 10% of the time I can move left and right. The actions are stochastic in this. If I change this reward, then reward is -1.1 for each step, right? So accordingly, I can decide what steps I need to take. If I change my reward to +1.01, then these actions are stochastic in nature, right? So the I will decide that, okay, my policy should be that the larger I remain in this particular arena, the more is the reward I got, right? Even in reaching to goal state. So I have to take care of these things, that my environmental model has a big impact on the optimal policy, and the reward has a big impact on the optimal policy. So these two things, your environment and reward structure. So as a programmer, we have to take care of both, right? If we control only the rewards, then again it's the issue that we will not be able to end up with the goal state always, right? So what we should do, we should always explore. So there's a saying that in a forest, if I encounter two road, then if I need to gain more, I should take the path which is less covered, right? It means I may be possible that I may explore some new things in it instead of going through the traditional path. So, but again, it should not be like that. Every time we need to follow that path, that traditional instead of traditional exploration path, right? So there should be a trade-off between all these: evaluation and instructive feedback, associative and non-associative type of the learning, or exploration and exploitation. So in case of exploration, let's say I go always with the greedy approach in that. So action chosen with the greatest estimated value, or your greedy action. So in that case, I go with the exploitation. So the in the matrix, if you remember of the bicycle riding, so if we go always by from left to right, so we call it as left to 90-degree or straight, then because we always go with the highest estimated value, so it is known as exploitation. But in some of the cases that works in that particular case, right, for the bicycle riding, but in other problem it may not work. So we have to search some other methods, right? So what we can do, we have one method as the epsilon greedy. It says that most of the time we go with the greediest action, and once in a while with the help of the probability, small probability epsilon, we can take a step randomly. We will explore, means most of the time we will exploit, and only if my probability is greater than 95%, let's say this epsilon value, then, or 98, then only I will exploit. But this situation may lead you to a dead end position. So I can use the another action method, that is the non-greedy action. It's in this case we need to explore more, right? So we have a concept of epsilon soft over here. The best action is selected with a probability of epsilon. Earlier it was the exploration was with the epsilon only. Now the best possible action will be selected only 1 minus epsilon, and rest of the time we will choose uniformly. Right. In the greedy action, we always go with the maximum value of Q with a probability of 1 minus epsilon only. In epsilon greedy, 1 minus epsilon. Mathematically, these are the way to filter, to control your exploration and exploitation so that we can trade off between them. Because this greedy approach or deterministic approach would not explore all the possible actions, right? So we need to try some new one in that. In case of epsilon policy, once in a while with that small probability that we discuss, you can take an action randomly, right? The drawback of this two method, epsilon greedy and epsilon soft, is that we are selecting the action randomly. So in case of softmax, this is the another type of the method for the action selection. So there are three methods total. Just a second. Okay, sorry. So in this case of the softmax, we can assign some weight with some actions so that I can have a trade-off between all the good actions and the bad actions. So a random action is selected with regards to the weight associated with each action in that, and the worst action is unlikely to be chosen in that case. While in the previous two cases, we can choose the action randomly. So your worst case or your best case has the equal probability. Right, so for softmax action, we can go with the epsilon weighting or the Boltzmann or the Gibbs action selection method, where this tau is your computational temperature. Right, so once I am having, I decided that what are the various actions that I can take, then let's talk about the another term, that is the policy. Right, so this policy at a particular step T. So pi t we called mathematically is a mapping from the state to the action, right? And the aim of our agent is to go by that policy which has maximum reward in it in a long term, right? So this goal and reward, the goal should specify what we want to achieve, right? Then we have the concept of the future reward, where we are having this RT with his. It's a combination of the different rewards, reward at T plus 1, T plus 2, and up to n step from that particular instance only. Then we have the discounted future rate. Why we use some parameter over here, this as a discount parameter, because the environment is stochastic in nature, uncertainty is there, partial observable, the may be possible that I am unable to understand the whole arena or whole environment, whole states, right? So let's say I want to send my Chandrayaan to moon. So we don't know all the environment of the moon. What we can do is we can simulate a similar environment with the help of some simulations at the earth, and then we teach our agent, right, or our robot, so that it can take a similar decision at the moon, right? So over there all the states are not visible to you, so it may be that it is partially observable, right? So we, to overcome such type of the issues, we have to use this discounted rate. Steve Jobs also says that whatever I am doing today, I am considering that this is my last day on earth, and then accordingly whatever the decision that I am making today, uh, on that basis only I'm making all the decisions, right? So it means I want to maximize my rewards, my action value. So this with reward, we also have a return. So this return is a reward in long term, right? Reward are your short term goal and returns are your long term goal. So as I told you that over here, we called it as a episode, right? So it's a subsequent or interaction between the agent environment, for example, the play of the game, trip through a maze, and likewise. So we can associate certain in one episode, I can associate the discount return as well. So geometrically, I can write mathematically, I can write the return as combination of different states where this row is my discount rate. So basically discount rate or return, what it tells the present value of the future reward, right? Then I have to update my weights according to that. So how I can do that? How I can do that? I can take the similar concept that we used to do in case of the neural network also, that the new or old state is equal to the new state is equal to old state plus some step size and the error in it, right? So how we decide over here, we go by the state value action and action value function. These are the two functions that are used to estimate how good it is for an agent to be in a given state. So if I want to apply the reinforcement learning on any application, there is some requirement. The first requirement is I should know what my goal is, right? Then I should know what my state are, right? Then what are the actions in that particular problem and how to assign the rewards. These are the four important things, four important prerequisites to solve a reinforcement learning. So if you want to use reinforcement learning in your problem, you have to explore all of these. These may believe me, if you have find this, so at least it will take 6 months to 1 year to find what should be the goal, state, and actions if your problem is new from the literature, from the experts. But once you identify these important parameters, then you can solve your problem easily using reinforcement learning, right? So there are different methods in the reinforcement learning. Dynamic programming is there, Monte Carlo method is there, temporal difference learning is there. This dynamic programming is used for the model based approaches. If the combination of both can be used in the temporal difference learning method. So according to your requirement, right, let's say I know the whole arena, right? I know all the states in it, then I will go with dynamic programming. If I'm unaware of the whole possible states, then I can go with Monte Carlo method. And there are certain cases where I can combine these two. I have a very limited knowledge of the model, and then I can explore again. So combination of both maybe come under this temporal difference learning. Q-learning, if you are aware of, it is part of this temporal difference learning only. Right? So based on the model, based on the value, based on the policy, you may decide what type of the reinforcement learning you can use. Right? So this is a taxonomy from a research paper. It's tells that the reinforcement learning can be used using two models. One is the model free based reinforcement learning or model based reinforcement learning. Right, so I have the policy optimization and the Q learning in that. So we will talk about this Q learning and this alpha zero in brief, because this is the deep reinforcement learning that actually uh, introduced the researcher that yes, using deep reinforcement learning, you can solve some real-time problems as well. Right, so in case of Q learning, it's a state action value function where expected return when starting in a state S, let's say over here, this is my starting state S. Then from here, if I take this action A, right, and I move to this next step S dash. So Q learning use any policy to estimate the Q that maximize the future reward, right? So you can use the Bellman equality equation in this. It is independent of the policy being followed. So my policy is decided after one particular episode. Right. So in that, as we discuss the equation of the updated or reward or updated value, it is equal to the old state plus some learning rate into the reward plus discount rate plus the maximum value attained so far. Right. So in case this Q learning is also known as the off learning. Off learning, why? Because we didn't change the policy, sorry, off policy. We didn't change the policy during the execution of this approach, right? So in this, the same, we use the old value, then learning rate, reward, discount rate, maximum future value, and your old value error. The another type of the learning is the on policy or the SASA policy. The off policy is known as the Q learning, that is very popular. On policy means during the updation, during the trial, you can change the policy, right? So it turn this into an account control by always updating the policy to be greedy with respect to the current estimations. You always have some kind of policy in that. So let's talk about these approach. Right? Let's take problem. I will recommend you to solve this problem with me so that you can understand what actually reinforcement learning is. We try to take a very simple problem and then we try to apply this reinforcement learning on that. Right? We write a program for finding the path for the bot using the reinforcement learning. So this is my arena. So what is this arena? In this, I am having 5 rooms, A, B, C, D, E, and within the building. And there is another outside area F. So I am having A, B, C, D, E, F, total 6 states in it. And each door is either open to a particular another room or the outside the building. And my aim that wherever my agent is, it should move or it should move out from this particular house. Right? The question is which path my agent should select. So any suggestion in this? What should we do in this? Yes. What path agent should choose? So what we can say over here is that we can convert this problem into some another way so that as a human we can understand, and then we can convert that understanding to the programming as well. So what we did, we tried to model this environment using reinforcement learning. So we convert all the rooms or this particular problem into the graph based problem. We represent the rooms by the graph where each room act as a node or vertex, and each door is an edge or link between one door to another door, and my final goal is F, right? So I told you that for modeling the environment, I have to select the goal. So I have already selected F as my goal. Then I need to assign some state. So all the rooms are my states. Each room act as a state, including your outside building. Then the actions over here is movement from one room to another. And your initial state, you can choose randomly. Let's say C is your initial state. And then reward. Right, so reward is the goal node. So what we can say that for every possible node we can assign that if I movement from one node to another node, there should be some value, right? So I have assigned 0 if there is a movement from one node to another, and if it lead to the goal state, then I have assigned 100. As a programmer, you are free to choose or assign any rewards, right? You can also assign from 10 to 1000. It's up to you. But generally, we go with from 0 to 100. That's why we follow that standard nomenclature. Right. So, based on the current situation, we develop one matrix. We call that as a matrix R or reward matrix. Right. So, as I told you in this beginning, that as a human, we are good with the patterns, but computer, they are good with the computation matrices. So we try to convert all this approach into the matrix form. So this is my reward table. So from A to A, I am not going to that. Not from A to B, again, no action can be performed, right? A to D, no action. A to E, there's a path, right? So I have given that as 0. So this is my reward table. Now let's talk about the metrics, experience metrics that we discussed earlier. So initially, my experience matrix or this experience table, or I call it as a Q matrix, right? It is 0 because I don't have any experience from movement from one particular state to another state. So this may act as your brain of the agent. So let's say total 6 states are here over here. So correspondingly, my size will be 6 by 6 in this particular case. So in more general case, it start with the 0 matrix of a single cell. Then we apply the Q learning on it, right? We start with the current state as your initial state. Then from current state, find the action that produce the maximum Q value. Then change your state from current state to the next state until you reach your goal. So with this, we have set our learning parameter as 0.8 and initial state as B. We set matrix Q as a 0 matrix initially because there was no learning, and the reward based on the conversion. So now let's see how Q learning works. So randomly I choose a state, right? So let's say I choose a state as B. Then from B, there are two possible paths. I can go to D or F. Now, if we consider F as our next step, randomly I can choose. I can go also choose D as well. But let's say we choose D. Then from F. Then from F we have three possible actions now, right? I can go to B, E, and F. So this F is my action state or the final goal state, right? So I can update my Q matrix now. So my Q matrix will be the reward of the state action for that particular value from B to F, movement of B to F. So it will be equal to the reward from B to F, that is the 100 over here. Then your learning rate, we consider it as 0.8. You may change it during the due course of time of iterations. Then the maximum value from movement of F to B, F to E, F to F, right? So this is, I will take this from the experience matrix, and in experience matrix all these values are 0 because I don't have any experience, right, over here. So now I have updated my matrix that whenever I will move from B to F, the value is 100. So this is my learning from this particular episode. And because this F is my final state, I can stop this episode now. Let's start again. So in that, initially, again, I choose my state as D from here. So now the possible actions from here is B, C, D, right? Then let's say again, I choose randomly as B as my next state. Then from B again, I can go with the D and F. So if I choose from D to B, then I need to update my Q matrix again, right? So it will be again from RDB plus some learning rate into maximum value from there, right? So now I have updated this BD as 80. Earlier it was 0. This whole matrix was 0 initially. With this second episode, I have updated it. But now because this B is not the final state, I have to repeat it again. So I repeat this task again. Right. So from B again, I can go to D and F, and let's say I select this F in that case. So F is my goal state, so I can stop. So whenever I will reach my goal state, then I will stop that particular episode. So if you want to apply this on the tic-tac-toe game, right, where we are having this 0 and X, right, possibility. So the game may end either by winning, by losing, or draw. So these are the possible final states, right? So there are three final states in this particular problem. So I told you that you have to select the goal state as well. It may vary from time to time. Okay. So if agent learn more and more experience through many episodes, then at the end that matrix table that was initially 0, 0 got saturated. There is no further updation in the weights. Right. So after this only we say that, okay, now that particular person is expert in that particular subject or field. Right. So we can normalize that. Again, this is the normalized Q matrix. Now, after learning, this is my overall learning, right? So now I can say, okay, by looking at just this particular Q, I can tell, oh, in whatever state you are, I can tell you the path, right? So let's say if you are at the C, then you need to go to D first. Then from D, because I am following the greedy approach, let's say, then there are two possibilities. You can go to B or you can select E. If you have selected B, then you should select F. If you have selected E, then again you should select F. So by looking at this, I can decide my path now. So these are the equal weightages. So this is how we can apply simple reinforcement learning on any problem, right? But the only thing you need to identify is the path, or the goal, the action, the states, the policy. These are the 4 things that you need to identify to begin with. So if we apply this type of simple Q learning, right, then if we apply this on this game, then in this case, I am considering the state as the screen pixel, and where my screen pixel is of size 84 cross 84. And I am considering 4 such frames, past frames. And the grayscale of each frame, because it's color image based pixel, screen is your pixel based features. So total 256 gray levels are there. So total number of the rows in the Q table will be 256 power 84 cross 84 cross 4 cross, sorry, 4. So this is much more than the number of the atoms in the universe, right? So for a larger set of the states, I am not able to apply the traditional Q learning in that. I should explore some other advanced method in it, right? So we talk about the deep learning. It's way of representation only. So we use the deep Q learning in it. So this deep Q learning, it uses a neural network to approximate the Q functions. So my state and actions, I fed them into the network, and correspondingly I get some Q value for it, right? So for this Atari game, just we talked, we can give the feedback using the different convolution in that layers, right? Then at the end, fully connected layers are there, and then accordingly you can take the decision. But over here, you can see that the number of the pixels corresponding to each convolution layer is much smaller as compared to the previous way of approaching. The advanced version of the deep Q learning is double deep Q network. In that, we try to use now the question is what will be my loss function, because I am using this neural network in it, right? So one Q value will act as your prediction, and another will act as your target in that. Then in case of the double QN, right, we can take, or it helps to reduce the biasness by introducing the inaccuracies of the Q learning at the beginning of the training. Right, so beside this, we are having the another version of the reinforcement learning, that is the AlphaGo. Actually, AlphaZero. This was a game. This was a problem or model to solve the problem of AlphaGo. Sorry.
Go is the world's oldest continuously played.
Go is a game similar to your chess, but the complexity of the Go is very, very high. There are much higher state as compared to the chess. And there are some countries, it is mainly popular in the China, in Japan. Uh, and over there are few generation who spend their whole time in playing this game. Like they start playing this from childhood, and they try to find all the possible states in it.
One of the simplest and also most abstract.
So some researchers from the Google, they try to make some programs in such a way so that it can beat this the best player of the alphabet. This is a whole documentary. So if you are more interested in this, you can also watch that. So that the game of the Go is very, very complicated. Like because of the number of the actions in it, like even number of the legal positions, it is somewhere to into 10 raised to power 170, right? So as a human also, it's very, very difficult to imagine all the possible.
Hello. Dr. Chandra sir, are you there?
For this,
Yes.
that's why I'll always prefer the previous mode.
Yes. But
Okay,
due to,
somehow we have to manage from this. Okay.
what to do? The situation is bound to us.
Yes. Let me share my screen. I was talking about the game of Go. So in that, as you have seen in that video, that there are,
Sir, please share your screen, sir.
yes, please. Is it visible now?
Yes, sir. Yes, sir. Visual.
So I was talking about this game where we have more than 2 into 10 raised to power 170 number of the possible positions, right? So this whole AlphaGo program, it was launched by the Google. They acquired DeepMind. DeepMind is basically responsible for developing the algorithm for this. So they try it for the different approaches, right? And they run it for many days, and then after that your program, this AlphaGo, it was even more powerful than all the existing systems that are there in this world in today's date, right? So with 0 day of the learning, there was no prior knowledge for the AlphaGo, but within this 3 day, it was able to compete the AlphaGo Lee, that was the hero of that particular game. Then within 20 days of continuous, it was able to reach the level of AlphaGo Master that defeats 60 top professionals online throughout the world. Then after 40 days, what it does, it tried to play with itself, and now we can say that it has reached to that level where AlphaGo beat even AlphaGo itself, right? So the outcome of this particular experiment was, if no doubt it will take some time to learn, like the way we also take the as a human, if we talk about the human, we also take some time to learn, right? In studying, you spend 20 to 25 years, right? Then after that, you are good in that particular field, and then you can propose new approaches, new solutions. So similar to that, my this reinforcement learning method, AlphaGo, right? It has a lot of potential for the commercial applications. So till date, it was not used in the real world problem, right? For the automated car, even for the robots operation also, deep learning was not involved. But slowly, because of the deep reinforcement learning now, we are able to control the different dynamics, right? As you can see this, so over here also we are using the reinforcement learning now. So now deep reinforcement learning is being used not only in the game based application, but also in the real time applications. So this is also an example of gate, where this robot tried to walk, right? Even in the adverse conditions. So slowly we are changing our approaches. We are trying to use it for the object detection. Earlier, we were not able to use it for the image processing, but now it is possible for the object detection, human pose estimations. As I told you, for electrical, financial marketing, it can be used. Now let's see how it can be used in the medical field. So I'm working in the motion analysis, so I will talk about that only. So in the gait analysis, we have one problem of the pose estimation, right? So when we walk, there is a repetitive cycle. So if we identify the pose, then we can easily identify the action. We can use it for the animations and the gaming based problems. It can be used for the old man care, basically geriatric care. Then it can be used to identify the abnormality in the gait patterns for the remote diagnosis, for the telemonitoring also. So pose estimation, there are different ways: 2D pose, 3D pose. 2D pose maybe or a single person or multiple person. Then in the 3D pose estimation, we try to formulate a model of the 3D single person or multiple person. So we have this pose estimation, and based on that we can say that there is some deviation it from the normal walking, and may be possible that within 1 year 2 years there may be some problem with the walking. So based on the depth and the occlusion, we can use the deep reinforcement learning for the active human pose estimation, so that we can develop a 3D model. At time t, the agent take the random viewpoints, then it select the next frame, and the agent decide whether to continue to the next frame or to stop the viewpoint selections. So in this way we can create a 3D pose of that particular object. My scholars are also working on this. They are in the implementation phase. But there are a lot of literature that says that we can use this for the post DRL method. Right, so that we can identify what is the intention of that particular person for activity recognition. Basically, it can be used in the crowd recognition if some mishappening may be there or not, or intention recognition also. You can use these different methods that are now available. The only challenge in applying the reinforcement learning to the real world application is that we don't have that much we didn't train our system that much, right? So what we need a simulation model for it, and then we can apply the different transfer learning, so that it can apply, it can work well when we transfer that learning to the real world application, right? So we need to improve the more simulations, so we can repeat our task once again. The best part in the reinforcement learning is, or any learning or any problem that you want to work, is that you start directly working on that problem, right? Then you will encounter some problem, try to resolve those problems, and then you will also see that how we can get good result out of that particular approach or in that particular problem. There are if you want to you are interested in reinforcement learning, then you can use different functions that are available nowadays. Python language has a lot of functionality for the deep learning as well as the reinforcement learning. So you can use the TensorFlow in that, right? So I will say that you try to implement the deep reinforcement learning by yourself, and then see how actually it is working. The In today's world, everything is online. There was a time when whenever we uh, go with some research, we used to hide our research part. But in today's world, as soon as I publish my paper, the researcher, they are more into the open source now, right? So it is being there. You can download from the GitHub. There are a lot of nowadays resources from which you can download the content. You can download the research papers. Even there is a website, code with paper, that give you the research paper as well as the code of that particular. The link is again with the GitHub only. But the takeaway is that if you are serious to solve a particular problem, you have a lot of scopes in today's world, lot of resources in today's world. So try to find the best resources that are available with respect to your problem, and then you can apply that approach. The problem that we solved in the today's session of the reinforcement learning, I have already uploaded it on the download section. So you may visit this website or this link, cprakash86, and then from there you can download the Python file of that reinforcement learning. So I will recommend that please at least try to run this program and see how reinforcement learning works, because it has a lot of potential in the different applications. In case of any query, you can mail me or you can visit my website. So with this, I end today's talk. So now I'm open for the questions. So if you want to ask any question, please feel free to ask the question.
Yeah. Thank you very much, Dr. Chandra sir. So dear audience, please, if you have any questions, please raise up your questions, doubts. So because today the last session of our Chandra Prakash sir. So you just, if you have any doubt, you can ping him or you can send a mail to him. Otherwise, you can ask also here. The time is with us, another 5 minutes. So I request all of you, please, if you have any doubt, you can raise your voice. I think Rahini Paroshe, are you there? Rahini Paroshe, are you there? You have raised the hand. Do you want to ask anything? Okay. So I think no one is asking anything. So we'll stop here, sir. Dr. Chandra sir, thank you very much for your cooperation. And irrespective of your busy schedule, because you are also busy with online classes and evaluations and everything. So now we are living in a different world, different environment. Everything is virtual, but irrespective of that, you have agreed and you have given a very good knowledge you have shared with our participants. And definitely, I hope some participants, if those are interested, they may work in image processing or any machine learning domain, so that they may contact with you. And from our side, definitely we'll discuss with you regarding the collaboration of some projects and other research directions. I will talk to you later on after completion of all this FDP program. So thank you very much. Thank you. Yes, yes, sir. Thank you very much for your cooperation, your support, your kindness of your knowledgeable words. Really, I am very happy with you. Thank you, sir.
So, sir, I would like to ask one question. Sorry for the late. Sir, gate analysis we are using. So it is ultimately we are going for the rheumatoid also. Okay. So the rheumatoid nodules we are getting as a rheumatoid nodules on skin. So at that time we can identify with rheumatoid nodule with intensity of the rheumatoid arthritis. Okay. So what aspects I can use to get the what that is a the duration of that nodule and age of that nodule and what aspects we have to go for that approach instead of going for the radiographic images directly through our photo or through our camera. How we can identify by using this image processing?
I'm so sorry, I couldn't hear your problem clearly because of some, I guess, network issue. Can you repeat your question?
Yes, sir. Ultimately, all things are data analysis or anything. It is ultimately going for the rheumatoid arthritis. So rheumatoid arthritis, we can identify by the nodules also, rheumatoid nodules, which is on skin.
Okay.
Though we have taken that, suppose for example, we have taken the image of that particular nodule, rheumatoid nodule. So how we can identify the age and the duration of that particular nodule, because every time we cannot continue observe the particular patient. So by using this image processing, how we can do this work? Because directly radiographic images, it will identify, but I don't want to take. Suppose one expert person is there. I'm just taking the photo of that. And I want to identify that all these things, extract that all features. What concepts I have to use? Because I've designed the proposal with different things, different concepts I use here. So one aspect I'm just lacking related to this. From image only, we can identify the health of that particular nodule. Is it possible?
Yes, there are many literatures that says that using the image only, we can extract some parameters, because there were certain there are in the earlier days there was very crude way for extracting the gait parameters. We used to have the sensors all over the body and tell the subject to walk, right? So if somebody tell you to walk in front of few person, then again my pattern got changed. So if you are carrying those sensors with you and then you are capturing the data, obviously it will change the gait parameters. So to overcome that, we have come to the vision based approaches. So I will suggest that nowadays there are various IS based sensors that you can also use. So there can be a mixing of both the vision based as well as the uh, IS sensors or the wearable sensors at least. That may help you in that. Now from that we can extract the feature. Another way is that I give my whole sample as it is to the deep learning method, basically the LSTM, let's say. Then it extract the important feature out of it, and then it can help you in your problem.
Okay, sir. Once it is sessions are over, again some points are there which I want to discuss with some photography I have it. So through mail I can maybe approach. Minimum,
Yes,
I
sure.
got some information about that one.
Still, I guess there is some issue with my network. I am unable to hear all your query. So I'm so sorry for it. You can drop me a mail. I will try to revert you with the whatever knowledge I have in that field.
Thank you. Thank you very much, sir.
Okay, thank you.
Okay, thank you, participants. Thank you very much for your kind patience to hearing the beautiful session delivered by our Dr. Chandra sir. So thank you, Dr. Chandra sir. Thank you very much once again. So whatever the rest of other formalities, I will communicate you over mail.
Sure.
Okay, sir. Okay, sir.
Sir,
thank you, sir. Thank you for inviting me.
Thank you. Thank you, sir.
Yes, you want to ask something, ma'am?
Yeah.
It is a very informative session. Very nice lecture is there. It is a research oriented openings are more. So thank you very much for this session.
Thank you.
Thank you, organizer also.
Thank you. Thank you very much. Thank you very much. So this is everybody's cooperation is needed to give the more beautiful scenario of all events. Okay. Thank you. Thank you all. So thank you once again, Dr. Chandra sir. We will communicate over mail to you for other formalities and for other communications. Thank you, sir.
Thank you for inviting, and thank you for listening.
Thank you, sir. Thank you. It's our pleasure. Thank you. Have a good day, sir.